Hi, and welcome to our video for Chapter 7. This is going to cover sections 7.1 and 7.2. So this chapter is very conceptual. There's a little tiny bit of math, but most of it is concepts. And the big idea here is that we're going to talk about why things are the way they are. We've learned a lot of topics, chapters 1 through 6. This chapter is going to help explain that, and it goes really well with chapter 8. The big thing here is we're going to talk about quantum mechanics and the quantum mechanical model of an atom. And in order to do that, we actually start by talking about light. Electrons are weird, and electrons behave a lot like light, so we use light to help explain them. Light has two components, an electrical component and a magnetic component. So they're both made of waves and they're perpendicular to one another, and all light travels at the speed of light, which is 3 × 10⁸ meters per second, and we abbreviate that with a lowercase c. Light travels much faster than the speed of sound. So when you're watching fireworks, or if there's a thunder and lightning storm, you will see it much faster than you will hear it. We use a few different characteristics when we describe waves. The first one is the amplitude, so this is the height of the wave, and I'll show you a picture on the next slide. The height is a measure of how bright the light is. The next one is the wavelength, and we abbreviate it with a lambda, and this is how long the wave is, wavelength. And we can measure this from the top of one wave to the top of the other. These are called the crests, or from the bottom to the bottom. These are called troughs. The next is the frequency, and this is abbreviated with the Greek letter nu, so it kind of looks like a fancy V. Frequency is how many waves pass a given point per second. So we can think of it as waves per second, but really its units are just seconds to the -1 or per seconds. And a seconds to the -1 is the same thing as a hertz. The energy is proportional to the amplitude and the frequency. So we generally lump these three together. The higher the frequency, the higher the energy. Wavelength has an opposite relationship. So a large wavelength means a smaller frequency and a smaller energy. And we'll do some math with that in a couple slides. Here is our picture to describe those words. So the crest is the top of the wave, the trough is the bottom, the node is anytime it passes the middle portion here. A node just means that it has no amplitude. Amplitude is the height of the wave, and then for the wavelength we can measure it crest to crest, or we could have labeled trough to trough as our wavelength. Can't really show frequency in a diagram since it involves movement. So here is the relationship between frequency, speed of light, and wavelength. And if we look at the units here, speed of light, constant, 3 × 10⁸ meters per second. Wavelength has to be in meters. Now wavelengths can come in a lot of different length units, so we have to make sure we convert those to meters. And then frequency has to be in seconds to the -1, which remember is the same thing as hertz. We're going to look at an entire electromagnetic spectrum. This one is just showing us the different colors of the rainbow. So the colors of the rainbow are red, orange, yellow, green, blue, indigo, violet. And if you've watched Bill Nye the Science Guy, then you might remember this as Roy G. Biv. Simple way to remember it, and you're remembering them in order. We'll talk a little bit more about that on the next couple slides. But the idea here is that there's two things. First is a white light is a mixture of all of the colors of the rainbow. And then the second thing is that an object will absorb all of the wavelengths except for the one that we see. So the observed color, in this case the apple is red, is reflecting the red wavelengths but absorbing all of the others. And then here's another one about the amplitude and the wavelength. This is showing us that the red, yellow, and blue colors have different wavelengths. That's why we get different colors. So red has a larger wavelength, yellow is in the middle, and then blue is smaller. And then the amplitude is just going to determine whether it's a bright red light or a dim red light. Here's the entire electromagnetic spectrum. So there's a lot of information on this. The top label is frequency. The middle label here is wavelength, and then we have energy also. So this is a small frequency, small energy, large wavelength, large frequency, large energy, small wavelength. So at the low energy side, radio waves, which include AM, FM, TV, cell phones, microwaves, infrared, this very, very small region of visible light, ultraviolet, X-rays, and then the highest energy are gamma rays. So this down here is just this tiny portion blown up so we can see it a little bit better. So our visible light goes from 750 nanometers to 400 nanometers. So our eyes can only see 250 nanometers of difference of light. There's a lot of other light out there that we just can't detect. When waves interact with each other, it's called interference. And there's two types, constructive and destructive. Constructive means that they add together, and destructive means that they cancel each other out. So if they are lined up, then they add together and they will have the same wavelength, but their amplitude is now larger because they've added together. If they are mismatched, meaning when one has a crest and one has a trough, then they're essentially canceling each other out and we end up with no wave. When light travels around a barrier, it bends. And we know this because if you have the light on in your bathroom and you're sitting in your living room, you can see the light in the hallway and probably all the way into your living room. The light travels around corners because it's a wave. So as it travels through the doorway of your bathroom, the light is still traveling. Now it's traveling in a diffracted wave instead, but it's still traveling. If it were made of particles, it wouldn't travel out in a diffraction pattern. We wouldn't get this wide berth. Instead, it would travel out in a straight line. So think of this, if you started throwing a bunch of stuff at the opening, it's only going to go out in a straight line. If you throw something, it's not going to turn the corner and end up over here. And again, we're talking about this because electrons behave like light. So they also take on that diffracted pattern. If there's two openings, then the diffraction will occur through both openings. As these waves run into each other, we're going to get constructive interference where we see the white patches and destructive interference where we see the black patches. We're going to talk about the photoelectric effect, which now is going to incorporate our electrons. The photoelectric effect says that when we shine light on a metal surface, electrons get ejected. And the idea here is that the energy of the light is directly related to its amplitude, its frequency, and indirectly related to its wavelength. So changing those pieces of information will change how much how much energy the light has, which would change how long it would take for the electrons to be emitted, as well as how many electrons get emitted. So here's our picture. The light hits the metal, the electrons leave. This is the way that it was measured. So light hits, electrons leave, it goes to a cathode, which the electrons are attracted to, and the voltage is registered, so we know exactly how many electrons have been emitted. Is how much frequency or the amount of energy that it takes to remove an electron. So there's a maximum wavelength that can be used to get these electrons to be emitted. So here comes Einstein, and Einstein says that the electrons have specific amounts of energy. So he said that they come in little packets called quanta or photons. We're going to use the word quantum, quanta, quantized a lot in this chapter, and it really just means that it has a set numerical value. And I'll remind you of that in a couple slides. We're going to look at a few more different things. But the energy is going to be directly related to that frequency and wavelength. And we've talked about this before, but this is the first time it's been put into numerical values. So here's Einstein's equation. Energy is equal to H. H is Planck's constant, so this is named after Max Planck. Its value is 6.626 times 10 to the negative 34th joules times seconds times the frequency. Or, incorporating the equation we used earlier, we can say that energy is equal to Planck's constant times the speed of light divided by the wavelength. So we have our variables in there as well as a couple constants to use energy, frequency, and wavelength all at the same time. So we're going to do a couple calculations with these pieces of information. To calculate the frequency of each wavelength of electromagnetic radiation, so 63.2 nanometers, let's get the rest of the questions up there. We're going to use this equation, frequency equals the speed of light over the wavelength. And I mentioned that our wavelength needs to be in meters, so that's our first task. So we're multiplying it by our nanometer conversion factor. This is one we'll use a lot in this chapter for the math. And really the easiest way to do it is just to tack on 10 to the negative 9th. We don't actually need to move any decimal places since we're not actually done with the math yet. And then we plug those values in. We have the speed of light divided by our wavelength. The meters are canceling out, so we're ending up with 1 over seconds, or seconds to the negative 1. So we get 4.74 times 10 to the 14th seconds to the negative 1. This one's the same but opposite. Calculate the wavelength of each frequency. So we have 100.2 megahertz. Same equation, just a little bit of rearranging. We need to turn those megahertz into just hertz. So again, we're using our prefix conversion factor of mega, which is 10 to the 6th. So again, I'm just kind of taking the easy way out here. 100.2 times 10 to the 6th hertz, which is the same as seconds to the negative 1. So I'm going to use seconds to the negative 1 because it shows the units canceling out. So 3.00 times 10 to the 8th meters per second, that's our speed of light, divided by the frequency. We have seconds to the negative 1, seconds to the negative 1. Those are going to cancel out, and we're left with 2.99 meters. And then in the last question it says, calculate the energy of a photon of electromagnetic radiation at each of the frequencies in 39 and 41. Now our equation for this did include multiple parts. We could have calculated this from the wavelength or from the frequency. Using the frequency is a little bit easier, just a little bit though. So energy is equal to Planck's constant times the frequency. So frequency times Planck's constant. Our seconds cancel out, and we're left with 3.14 times 10 to the negative 19th joules. Here's our frequency times Planck's constant, 6.64 times 10 to the negative 26th joules. So really it's just rearranging those couple of equations and solving for that missing piece. Last question. A heat lamp produces 32.8 watts of power at a wavelength of 6.5 micrometers. How many photons are emitted per second? And then it tells us that 1 watt is equal to 1 joule per second. So there's really two pieces of information here. This is the wavelength of the individual light waves that are coming off of the lamp. And this is the lamp as a whole, how much power it's producing. So these are all of the wavelengths put together. So we need to do a couple things. First, we need to determine the energy of one photon. So we're going to use this equation. So the energy is equal to Planck's constant times the speed of light divided by the wavelength. We know the wavelength. It's not in the right units. It's in micrometers instead of just meters. So again, we're going to use our prefix. Micro is 10 to the negative 6th. So we have Planck's constant, the speed of light, the wavelength, 6.5 times 10 to the negative 6, so I converted it to meters instead of micrometers. Seconds cancel out, meters cancel out, and we're left with joules. And really, this is joules per photon or joules per wave. Then we can use the energy of the lamp to convert how many photons per second we get. So we're starting with the number we just figured out. There's one photon for every 3.05 times 10 to the negative 20th joules. This number was given. 32.8 watts of power is the same thing as 32.8 joules per second. We're given that conversion factor in the problem. So when we set it up like this, the joules cancel out. We're left with photons per second. 1.07 times 10 to the 21st photons per second. This is a common type of problem, and really this is the last step of any of those problems, is using the energy of an individual photon and the energy of the entire lamp to make that last conversion. Last slide. So looking at the photoelectric effect and the metal that's ejecting the electrons, one of the things that had to be overcome is what's called the binding energy. This is how much energy the electrons are using to hold on to that metal. So in order to escape, or in order to be ejected, the energy that they're taking in has to be more than the binding energy. So the energy of the photon minus the binding energy is how much kinetic energy the electrons will have in order to leave. So the kinetic energy is equal to Planck's constant times the frequency of the light, because that's the energy of the light, minus this guy. So this abbreviation, which I believe is a phi, I didn't look it up beforehand, so I don't remember off the top of my head, but I think it's called a phi, is the binding energy. It's another one of our Greek letters.